We talk about our transducer beam widths, and typically transducer beam widths are defined at the half power point, the point at which you get to half amplitude energy as you move kind of down that beam pattern. And typically if you look at beam plots with your calibration, if you get it, your 15-degree transducer may spec as a 14.1 or a 15.2. It's sort of they're definitely consistently built with the elements, but there's always a little bit of a variation even within a lot or so on. But there's that's how they're defined. But for a single beam transducer, the effective beam width over which you're going to detect a fish is a function of that transducer directivity, that how that element is built, the diameter of that element. Really, you can think of that as the focus of your flashlight, and the target strength of the target, and that is a larger fish, a bigger reflector, will be seen further off axis than a small fish. And we've seen this before. Transducer beam doesn't really look like this in the water, but if you were to, when we calibrate in the calibration barge, there's a test transducer and then a fixture that swings the test transducer across the reference transducer and measures what that response of the transducer is, and then this 3D representation of it. And that concept that transducers do have side lobes right at the axis of the transducer, for a given threshold. Say you're set up for to detect a minus 56 dB echo is your smallest threshold. Really, that beam width is just breaking 0 degrees as you move above that 56 dB target, and then as you get out to 6 dB down to your minus 50 dB fish, then your beam width would be that nominal beam width, and and then as you get into larger fish, and this next I think slide shows that a little bit. This is just a cut showing that for a different target strength fish, again with a single beam system, as you get into larger and larger fish, you can see them further from the acoustic axis, and of course that's kind of a problem for quantitative assessments. Same thing for your fish finders that are using single beam transducers. In the early days when we were doing salmon smolt work on the Columbia, we'd actually either do some netting or had some of the early dual beam systems that could measure target strength. These were salmon smolt that were fairly uniform in size at any given time, but would change over the season. And we'd take that information each week, look at the polar plots for the transducer and determine what the effective sampling volume was. But with split beam systems, that's really what's given us a lot more power over controlling our sampling volume. Like we just looked at earlier when we went through the DEP menu, we can set off-axis angles, maximum acceptance angles, and if we get echoes outside in the beam pattern of those of that domain, they're just not going to be written to the data record. So that's great. We can define a sampling volume, and we don't need to really go through this. That's just the whole method the split beam system uses to position fish, where it transmits on the single element, and then that element's divided into 4 quadrants on the receive side when those echoes come back, and then what that graphic's showing is from the phase, the arrival time, really the angle that returning sound front is encountering the transducer face. It can get a left-right and an up-down or bow-stern angle, and then position that fish in the beam. So anyway, we've probably got variations of this formula in all of our different beam weighting formulas, just that, for a cone, 2 times the range times the tangent of half the beam angle is the width or the diameter of the the beam at any range. And when we're doing tracked fish work, we typically do, because we've got increasing probability detection with range as the beam spreads, we use that in our weighting, but that defines that. And so we can see here just kind of an overlay of that polar plot or beam response plot, with just kind of showing that restricted split beam sampled volume kind of within the main lobe. We do still get for fish within 6 decibels of your minimum detection threshold. You can kind of see that a little bit just visually in that illustration, with below that kind of half power point down to the 0 dB point. You do have still have a diminishing beam volume with target size, down to where, say, you had a minus 55 dB on axis echo detection threshold. That's your beam volume for that is basically approaching, or your angle approaching 0, and you can correct for that. So anyway, so we can define a precise transducer beam width and an acoustic sampling volume with our split beam system. So that's great. What's the deal? And we've talked about this a bit before, but that requirement for target tracking, just if you've got noise or other scattered individual echoes surrounding your fish, you don't want to you don't have high confidence whether those are originating from a fish that just grazed the edge of the beam, or a noise echo, or a big plankton or a particle. So we require some minimum number of consecutive, or not necessarily consecutive, but at least spatially associated echoes, our tracks, during data processing. Typically, 4 echoes are commonly used. Once in a rare while, if you're in a real high velocity environment or just are pushed into it, I've used 3, but you can start to get to where you'll get noise that could line up in that way. Sometimes riverine upstream salmon studies, you might set your minimum much higher than that, but that does establish a minimum chord length through this cut through the beam over which you can detect fish, because there are areas on the edges of the beam that just don't have chord lengths long enough to return those number of echoes. So we don't have to focus too much on math, but you can calculate out for your 15-degree transducer, or a transducer of some given beam width, what the average chord length of your fish through that beam at that range would be. And this gives kind of a graphic illustration. Just you can kind of see on the top there that say we're requiring four echoes, and the length of that chord is going to be based on our boat speed, the diameter of the beam at the depth of detection, and then you can calculate your percent detectability as d sub t, is that measure of your effective beam width as a proportion of the nominal beam width, the whole width across the full diameter. And we've shown some of these before. I think I've even given some number of you guys the little Excel sheet we've got for this, and people have a pretty good handle on this. But you never totally reach your nominal beam width or your 100% detectability, although you basically get at some range where your beam is large enough or given a fast enough ping rate. You'd like to be working up in the flat part of that curve is basically the take home. And so this example just shows for kind of an odd one, a 13-degree beam width transducer, 10 pings per second, assumed fish velocity, which for us it would relate back to our boat speed. And you can see at some closer ranges your effective beam width, over which you could track a fish target and get 4 hits at it, is somewhat reduced. And at a range closer than 5 feet in that example, you wouldn't have any chord lengths that you could meet that. And then just looking at increased velocity, we see that depth at which we could first resolve fish moving out to sort of a 13 meter range. And this is at a 7.5 foot per second velocity, the same parameters as the earlier one. So kind of see that curve's not as flat up in kind of that mid range, and have some reduction in the effective beam width. So target strength relative to the minimum echo detection threshold, we looked at that in kind of the early slides, where that you can get some reductions in your sample volume for very small fish. We can totally dodge that one if we collect to a minimum echo detection threshold that's at least 6 dB smaller than our smallest size fish of interest. Fish transit velocities or boat speed, the range of fish from the transducer as it spreads, we get bigger percent detectability across the beam. There are also effects, not so much of an issue in most mobile surveys, although I guess it could be to some extent in a horizontal transducer, as fish are moving through the beam in quartering angles and or dive angles in a down-looking transducer in front of a dam. That has a difference, or has an effect. It typically increases the chord length through the beam. Transducer beam width, wider beam widths will usually step up to that kind of flat part of the curve a bit quicker than a narrower beam width for a given set of parameters. And then transducer orientation. We already talked ahead of that, just trying to work in that flat part of the curve. Running at faster echo sounder ping rates, if your depth will support it, helps that effective beam width to essentially be equivalent to your nominal beam width across the ranges you're interested in. You can, again, looking at these models, you can do range-dependent weightings too. I have done it. Ideally, it's nice if you can set things up to where you don't have to. But if your effective beam width is significantly smaller in an area you're interested in detecting fish in, then using that as in your weighting factor would be the most accurate way to go. Another trick you can do, and you saw that maybe in the example I was showing in the DEP setup earlier, where I'd actually opened up my acceptance angles slightly on the 15 degree, run the detectability model to where over my range of interest it was basically centered on 15 degrees with not a lot of variation, and then I used 15 degrees in my weighting on those tracked fish. So there's limits to how far you can open up the beam, but there's enough give certainly on a 15 degree to go plus or minus 20%. Certainly anybody who doesn't have it, happy to share the spreadsheet. I have this linked, but we don't have to play around with it too much. But this was just an example from that Cherry Point survey where I'd opened up the acceptance angles to 16 degrees and then just modeled that through to where its effective beam width is basically centered around 15 degrees.